If you want to find the first time people used geothermal energy, you've got to go back a long way. You've got to go back before the first geothermal power plant in the Tuscany region of Italy from 1904. You've got to go back before the first geothermal district heating system in France in the 14th century. You've got to go back before geothermal space heating in Pompeii, back before heated baths in ancient Rome, all the way back to the early evidence of indigenous people right here in Canada using geothermal heat for cooking over 10,000 years ago. Geothermal just might be our oldest, most consistent source of energy. But what if it could be our future? What if geothermal energy could be the clean, renewable, constant energy source we've been looking for? The very same one we've been looking at for more than 10,000 years. Today, in the second of this two-part series, we sit down with John Redfern of Eavor Technologies to discuss a new breakthrough in geothermal energy here on Carbon Copy. Let's start with the basics. What is geothermal energy and how can we make use of it?
Geothermal energy is basically any energy pulled from the earth itself in the form of heat primarily. There's a variety of different forms of geothermal energy. You can have a geothermal heat pump known as geoexchange, where you're just using the near subsurface as a latent heat sink for a heat pump. Then you have traditional geothermal, which is usually just harvesting heat for district heating or things like that. And that's done by searching for a aquifer the same way in oil and gas you'd search for an oil and gas reservoir. And it's involved finding that subtle reservoir, that permeability in the subsurface, and then producing a fluid to the surface that you either produce as oil and gas or you produce as a hot brine that you use for heating, and or converting to electricity by going through something called an organic Rankine cycle engine.
I understand that you and your team have developed a new innovative solution for harnessing geothermal energy. Tell me about the Everloop technology.
Well, our technology is different, and we like to say there's a bigger difference between our technology and traditional geothermal than there is between traditional geothermal and oil and gas. That's because, as I alluded to earlier, both traditional geothermal and oil and gas involve searching for, discovering, delineating, and producing from a reservoir. It's either a brine or a hydrocarbon. We take out the reservoir out of the whole process by just harvesting heat by conduction only without producing a fluid of any kind. And how did we do that? Where did we come up with that? Well, we came up with that because we weren't geothermal people to start with. We were oil and gas people. We were people who are used to doing other tech startups. And we only got into this because we were asking a different question than a traditional geothermal proponent. Usually geothermal is saying, how do I find better geothermal resources? How do I produce them at a higher power? How do I just drive down that cost? They're all thinking in terms of producing hot brine. We started out by the simple question, being in Alberta, we said, geez, is there not a better use for all the suspended but not yet abandoned well sites in Alberta? We've got, I won't say dozens, we've got tens of thousands of them. That represents a huge liability to restore those to their natural state. And we said there's got to be a better use for this other than just turning it back into grassland or farmland. And a lot of people, one of the first things we thought of was geothermal. We thought maybe we could reuse the wells. It took us about a month to figure out that wasn't going to work. But that got us onto the question of, why does geothermal not work everywhere? Why does it only work in a few ultra hot places? And when we started to look at that, that's when we started to ask different questions. Not how do we find a hotter, better resource, but how do we make geothermal work in a place like Alberta? That's a sedimentary basin that's relatively low enthalpy or low temperature, as you would call it. And what are the things that are holding that back? And at the start, we Like any good inventor, we had very little knowledge, so we were asking lots of naive questions. But one of the things we noticed was that when you're dealing with a low temperature environment, just to get the water in and out of the rock, then bring it to the surface, extract the heat, and pump it back down into the reservoir required a lot of energy. And because you weren't taking that much energy out of it, you were losing between 50 and 80% of the power in parasitic pump load, which obviously killed the economics. So that started us asking, how do you get rid of the parasitic pump load? And by doing that, that's when we had, or my co-founder actually had the idea. Paul Cairns said, he's a finance guy, so he was uninhibited by engineering concerns. He said, to get rid of that parasitic pump load, what if we just drilled 2 wells down, turned towards them, and connected them toe to toe, and created this big U-loop that we could tie back at the surface? That would make a nice little loop that we could flow the water through without resistance. And myself and a bunch of other people said, that sounds like a terrible idea, but I'd done lots of startups with Paul before, so I said, but let's test it out. And lo and behold, when we started talking to some engineers who knew a bit more about this, they said, actually, it's not that bad, because not only are you reducing the parasitic pump load, you're setting up something here called a thermosiphon effect, which will pump itself. So that, the inlet well, with the water going down, it'll go down cold, it'll get heated up, and it'll come up hot. So on one side, you have a 3-kilometer column of warm water, and the other side, you have a 3-kilometer column of cold water. The cold water is more dense, so it sets up this thermosiphon effect that pumps itself. So that was the start of the whole company. And from that humble beginning, we still realized what we had created was not economic yet, but we said we liked the loop concept. We liked the idea of creating this closed loop and not being reliant on the reservoir. And we started to ask ourselves, how do we make that closed loop better? And that's what we've been doing for the last 3 years. So that caused us to ask some questions. How do we make this loop concept better? And again, we got lucky, because in Alberta, we are in the right place to search for that answer. Because when you look at what we do well in Alberta, well, we do oil and gas well, that's for sure. And we have taken part in the whole, directional drilling, horizontal drilling revolution that has opened up shale gas and shale oil and all that sort of stuff. The resource plays involved there. But we're also have a lot of experience in the oil sands, some unique experience. And what does the oil sands entail? It entails drilling down and creating a lot of multilateral wells, where you got one vertical well and up to 40 horizontal wells off of that. And what do you use those wells for? Well, in a SAGD environment, you use them to pump steam to add heat to the subsurface. So we have a lot of engineers who are used to drilling multilateral wells, and a lot of engineers who are used to calculating the thermodynamic properties of getting heat into the rock. All we asked them to do is, why don't you reverse that process and help us figure out how to economically extract heat from that same rock? So we've got a bunch of people on our team from places like Synovus who have a lot of experience in that, and they said, hey guys, take that loop concept you have, but instead of having 2 vertical well bores attached by a horizontal well at the bottom, why don't you have 10 or 12 of those horizontal multilaterals connected to the same 2 vertical well bores, the same vertical well pair? And that really increases the capital efficiency of the entire thing, because you're not replicating those vertical wells. And these same people came up with the idea of, why are you casing all those multilaterals? You're not producing fluid into a well-bore. You just want water to go through it so that it can take heat out of the rocks via conduction. And so we found a way to finish all those multilaterals without putting metal casing in, and instead having a special form of sealant that we call rock pipe that in and of itself cuts 50% of the cost out of the development.
I must say that's brilliant, but help me understand a couple things. And so to set up my next question, I just got a couple actually sort of quick sub-questions. The first is, how deep do you drill vertically?
Okay. Traditionally, most places in the Earth, you have a temperature gradient of about 30 degrees C per kilometer. So to get down to the minimum temperatures we have in an average place, you have to go down 3 or 4 kilometers to do a heat project or to do power project at the limits of viability. Obviously, I can talk to you a little bit later about some other technologies we're developing where we're talking about going down, 6 or 7 kilometers to hotter, deeper rock. But so it's anywhere in that range, anywhere from, well, actually, it can be shallower too, because in some areas of the world, it's incredibly hot. Certain places in Nevada and California, for example, or in Japan, some places we have heat gradients of over 100 degrees C per kilometer. Obviously, you don't have to go down as deep in some of those places, but so anywhere from 1 kilometer to 7 to 8 kilometers. But it's way deeper than your average, let's say, geothermal heat pump, where you're going down 30 meters or whatever.
And then how long are the laterals?
The laterals can be, 2.5 kilometers as they are in our demo project, but they'd be more likely to be about 3 to 5 kilometers in length. And of course, as we perfect the technology over the coming years, we hope to be able to make them even longer. But off one vertical well pair, if you have 10 multilaterals and they're each 5 kilometers long, that's 50 kilometers of subsurface wellbore. So it is truly a massive radiator, and that's what makes it work.
So help me understand this. You drill vertically 2, 3, 4, 5 kilometers, and then you have horizontal wells coming out of those verticals, and they're, another 5 kilometers long, again, horizontally. How in the heck do you make sure those wells meet up in the middle?
Yeah, that's part of the magic, but actually, it's easier than you'd think. The technology exists already. You already have directional drilling. You have a fair idea, sort of an ellipse of uncertainty as to where that well is to start with. And then you have some magnetic ranging technology that you put in the bottom hole assembly itself, and that can detect where the other well is up to about 130 meters away. So you just got, when you're taking the two wells down and drilling, a few kilometers down and a few kilometers over, you've got to get within 130 meters, and then you can see, basically, you're pinging, you can see where the other well is, and you can steer right into it. And of course, you don't have to hit, directly head on, toe to toe. As long as you're close, you can slide in slightly, somewhere along the first, 10 to 20 meters of that well.
You talked about the thermosiphon effect and its importance in terms of driving the flow of fluid through the wells. How do you know that the thermosiphon effect will happen?
How do we know the thermosiphon effect will happen? Well, the easy answer now is because we've done our Everlight demonstration project, and it happens. But that was always a question we had before, where people would say, how do you know for sure? Well, it's really 19th century classical thermodynamics. We know how fluids behave. We know how the density changes with temperature. It's simply mechanics. Now, our guys have built, and third parties have built to test that, sophisticated computer models where you model it all out in detail. And I'm happy to say that whether it's the models we made ourselves or third-party vendors did, or TNO over in the Netherlands, or even the federal government scientists themselves, they've all gone back and modeled, the situation and come up with almost identical answers to ourselves. Now, the harder question is not whether the thermosiphon itself will happen. I think everyone's agreed that's obviously part of the reality. It was more a question, there was a lot of uncertainty where people worried that the reservoir would cool off too quickly, or how did we know the power output was going to be what we forecasted? And again, the easy answer is to say, we've done the demo and it came in within 2% of what we estimated. Now, the fact that it's a slow, gentle process without many variables attached to it, because we don't care about the rock much, we don't care about permeability, we don't care about any of these subtle things that people use very sophisticated tools and modeling techniques for in the oil and gas and traditional geothermal market to predict what's going to happen. All we care about is the thermal conductivity of the rock, which doesn't vary that much, and how fast we can drill it, and what the temperature gradient is. Those are all fairly predictable, and knowing those, we can not only predict the output within, a few percentage points, but we know how it's going to react over the long term, over 30, 40, 50 years. We tend to design our well configuration so it's about a 30-year plateau, and then it declines at about 0.2% after that. So these are long-lived assets. So even so, the initial gut reaction of most people is that really going to work, and isn't it not going to cool off too quickly? And there's way too much uncertainty, is there not, in doing something new like that? Actually, the big advantage of our system is it's easy to predict ahead of time. It's certain you know what you're going to get, and you know what you're going to get pretty damn accurately, looking out into the future, decades to come.
How much is an outdated facility costing you? Whether you're upgrading your equipment, your building, or finding an alternate power source, the upgrades you do now will lead to long-term savings. With the Energy Savings for Business program, Emissions Reduction Alberta is investing $55 million to keep Alberta's small and medium-sized businesses competitive. Emissions Reduction Alberta will cover up to $250,000 on projects that lower your costs and lower your emissions. In a province where local skilled trades have the expertise needed to do these upgrades, it's an investment in your small or medium-sized business and our province. Energy efficiency means more jobs, lower overhead, and a better Alberta for all of us. Find out more about the Energy Savings for Business program at eralberta.ca. On one hand, you've got this exciting new technology for geothermal energy that builds on Alberta's expertise in horizontal drilling. On the other hand, the idea of capturing geothermal energy is not new. Tell me why this is the right time now to scale up and test the Everloop technology.
Well, it's the right time now because we haven't had these building blocks in place. Even if we had the idea for the Everloop, 5 to 10 years before, the economics wouldn't be there. The drilling technology wouldn't be there to complete that in a cost-effective manner. So partially it's timing. I know as well it's also good timing in that there's lots of resources, skilled personnel, assets, and everything else that can be reapplied to the geothermal sector who are finding a harder time getting profitable projects in their original oil and gas domain. So we're a nice transitionary technology or solution for oil and gas people. But the main thing is it just wasn't capable before. And we also like to think that maybe people just didn't think about it before either. But up to now, geothermal, it has been around for about 100 years. The original geothermal power plant in Italy is still running after all that time. And it's always sort of been a very attractive option in that it was always billed as green and it was billed as baseload. Whereas, other green solutions tend to be intermittent, the scalable ones anyways, like wind and solar. So this was viewed as a nice complement to that. We were actually down talking to Duke Energy, and they were talking about something like called a Zephyr. We said, what we really want is a Zephyr, but they don't exist. And we go, what the hell's a Zephyr? And they said, it's a zero-emitting, load-following resource. Doesn't exist. We said, that's what we got. So, we started out, very interestingly, just trying to find a use for orphan well sites. We ended up getting into geothermal, and then we ended up figuring out how do we make geothermal work in Alberta. We then leveraged Alberta's natural advantages in that because of all their thermodynamic work and multilateral drilling in the oil sands. And then we ended up realizing that we weren't even just figuring out how to make geothermal work in Alberta. We were figuring out how to make a Zephyr. We were figuring out how to be the first product that was scalable, green, and dispatchable all in one. And that's how we stumbled into something truly exciting.
I understand that you're operating a pilot project right now. Tell me about that project, what you've accomplished so far, and what you still hope to accomplish with the pilot.
The pilot, we wanted the pilot to be here in Alberta because it's one of the cheaper places we could imagine. And Alberta and the States are going to be the cheapest places to build Everloops. They're just not the place to get the highest priced power in the short term. And we wanted to build that in Alberta because we wanted to work with our local service company operators to build, an ecosystem that could follow us when we go internationally to build Everloops elsewhere. Like I said, some of the first commercial Everloops are likely to be overseas. But we first had to do the demo project. And what was the goal of the demo project? It wasn't to produce a particular amount of heat or power. It was to answer the questions that our prospective clients had already had for us. So whether we were talking to people in Japan or Europe or elsewhere, the key questions they had is, okay, you've proven to me conceptually how it could work. Now prove to me that you can take all these sort of building blocks that you've taken from other areas and string them together in a way that works collectively. And in particular, they wanted to see a few things. They wanted to see that we could intersect the multilaterals toe to toe. One of the things you asked for before and saying how the heck do you do that? So they wanted to see that intersection proven in a multilateral format. They wanted to see our sealant work so we don't have to case the well bores. So that was our rock pipe technology. They wanted to see that demonstrated. And they wanted to see the thermosiphon work, and most importantly of all, they wanted to see our thermodynamics models proven in the field. And they wanted to see that we could do the whole ball of wax on time and on budget. And, I'm happy to say we've ticked all of those boxes.
Have you learned any important lessons or had any breakthroughs in operating the field pilot?
Yeah, I mean, there was a number of things. Every time you have something sort of perform slightly differently than expected, you have some learnings. And a lot of the stuff that we've learned hasn't been fully patented yet, so I won't tell you about it. But a lot of it, for example, that was unexpected was the dispatchability of the system. We knew it was going to have some ability to do that, but only by actually operating it did we realize how flexible it was.
Tell me, what's next after this pilot project?
What's next is we're totally focused on commercial implementations. Our first one is one in Bavaria, in Gerets Ried. Again, what's interesting when we talk about how we're taking this solution of ours to make geothermal an anywhere solution, a scalable solution, a solution that can go where traditional geothermal didn't go before. Our project in Germany is building off I won't want to say failed, but a unsuccessful traditional geothermal project there, where they drilled down, spent 10 or 11 years and quite a few tens of millions of dollars on drilling a couple of hot but dry wells, so that are of no use for traditional geothermal, but we can make use of them. And we've got prospects like this all around the world, in the Caribbean, in Japan, where people have spent $20-30 million in a good decade trying to make traditional geothermal work, and yet we can come in and, we believe, make it work in 18 months to 2 years in an area that was thought impossible before. Of course, we're not just doing it in failed in locations where there's been a failed traditional project, but those are the areas that are quickest to market, because so much of the advanced work, laying out the drilling pad, doing all the environmental assessments, lining up the offtake agreements, doing the geology, liaising with the local community. In all of these projects, that's already been done, and we can sort of slip in and complete the last mile with our technology.
So we're exporting a made-in-Alberta solution to help the world decarbonize. Is that correct?
That is correct. And it's happening first here, but the first really scalable options to do that, unless the regulatory regime changes and the electrical market changes a bit here, the best early places to do that are in these high feed-in tariff markets.
I'm wondering if you could tell me, how has funding from organizations like ERA helped get the Everloop technology to where it is today?
I mean, we're obviously very grateful because we did get considerable support from ERA, from Alberta Innovates, from NRCan, and from STTC. So 2 of the federal agencies and 2 of the provincial agencies, and they deferred a lot of the cost of building that first Everloop demo here in Alberta, which helped showcase the technology, helped prove up the technology. And without that sort of support, it would have been much more difficult to get where we are today. So they provided a very valuable bridge between the theory of what we wanted to do and commerciality by funding collectively, those four organizations collectively funding a large percentage of that first demo project. And a similar sort of effort for the first commercial project could make sure that that project starts here and finishes here as early as anywhere else. So it's a good precedent, and we're good partners with all four of those agencies. They were very supportive, and it all went off, I think, without a hitch on both sides. I think ERA and SDTC and Alberta Innovates, all four of the agencies were happy with the results they got.
Is there anything else that you want to say or didn't get a chance to mention?
We're just excited that we have this opportunity to make this sort of impact for Alberta and for the country and the world. And we know a lot of it's fortuitous, but we think it's just amazing the way the skill set here in Alberta came together with the problem here in Alberta, the orphan wells, and ended up unexpectedly catapulting us into this much larger global opportunity. And we're certainly going to run with it as fast as we can. And what we are doing is whether or not the first commercial project is here in Alberta, we are developing all our R&D and all the sort of white-collar jobs supporting that and driving that forward are mainly here in Alberta because we got a great skills base here and a lot of very motivated people who are looking to transition their skills on the green side. So this wouldn't have happened unless we started asking these questions in Alberta and developing and doing the first sort of research here in Alberta. Now, of course, it's turning into more of a global effort. We've got research going on in France, so in Norway, down in the States, all in various places, all to bring this forward. But it all started here in Alberta, and the core team is still here in Alberta, and will remain that way. And we're just hoping we can, move beyond and do the commercial projects here as well too.
Thank you, John. It's been an absolute pleasure.